Hey chemistry students, we are moving on here to video 6.3 where we are going to compare ionic and molecular compounds as well as briefly touch on some more characteristics of molecular compounds. So first and foremost, if you don't know already what an ionic compound is, here is your definition as well as the molecular compound. You're more than welcome to jot these down if you would like to. Also, if you would like to pause the video to get down the characteristics of ionic compounds. Basically, you need to know that ionic compounds are crystalline solids at room temperature. And to be completely honest, for the most part here, so are molecular compounds as well. So molecular as well for solids at room temperature. They have a higher melting point and boiling point when compared to covalent compounds. Covalent compounds here are your molecular compounds here. So this is a good review of what is a molecular compound. Is a covalent compound. So two non-metals being bonded together. That's a non plus a non-metal being bonded together. They do conduct electrical current in molten or solution states. So if something is a solution, remember homogeneous or homogeneous solutions, that is when you have a solvent and a solute. So if something is soluble, that means it can dissolve in water. So again, if you did not know that, dissolve in water. So H2O is our solvent. Are extremely polar bonds. So when we're dealing with those electronegativity differences here, an extremely polar bond is going to be greater than that 1.7 value on the electronegativity difference. As far as soluble in water, I just kind of hit on it there on a solution state. Soluble can dissolve in water, not soluble in non-polar solvents. All right, so water is a polar solvent that makes it able to dissolve ionic compounds such as different salts. Let's go ahead and briefly talk here about some molecular compounds. Molecular compounds, and I want to briefly touch on these diatomic molecules. You need to know these seven. There's 7 of them. H2, F2, Cl2, Br2, I2, C2, and N2. Those are the 7 molecules, diatomic. Di meaning 2, atomic atoms, 2 atoms bonded together. That's how they naturally occur. When you find them in nature, they do not occur. So hydrogen does not occur as just H. That's no. It occurs as H2. So as F2, Br2. They all occur as 2. And you need to remember here, this is a molecule, all right? So just to reiterate here, since we're talking about some molecular compounds, this is a molecule. These are basically make a 7 on the periodic table. So if you're looking at the periodic table, here's an image on the periodic table where you have nitrogen, oxygen, fluorine, and then down group 17 here. So most of the halogens. Don't forget about hydrogen, which would be up on the far left corner, but you need to know those. They naturally occur that way. Now briefly, going back here, talking about the Lewis dot structures. One thing I forgot to hit on was resonance and resonance structures. So the definition here of resonance, when we have a molecule that can have different Lewis structures. Here's your example, and basically the only time you're going to see this is if you have a double bond and a single bond. So just remember, double plus single bond in the same molecule is basically going to lead to resonance. Example, double bond is on the left, but you could basically take it and flip your molecule over. The double bond would end up on the right. So it flips from the left to the right. It's the same compound, just the bond can occur on either side. So again, the only time you really are going to see this is if you ever have a double or single bond. Again, I'd like to compare a little bit more here between ionic compounds and molecular compounds. Table salt or any other salt And a salt is basically going to be, any ionic compound, again, is a metal plus a non-metal. And a molecular compound here are basically our non-metal plus a non-metal. Here's a molecular compound where you have many, many different small parts that are going to be bonded together to form a large molecule. Ionic compounds, however, form more in a crystalline structure, which we're going to talk about on the next slide, where we have specific atoms in specific places with our positives and our negatives here attracting to form these bonds. This crystal lattice that I just briefly mentioned on, you don't have to know necessarily exactly what the crystal lattice is, but know that it basically is an orderly arrangement of atoms for ionic compounds. So here we have our sodiums and our chlorines. In this example, I believe this is another example of table salt, so NaCl, with our positive and our negatives being attracted. But if this was chlorine minus and this was chlorine minus, there would be some repulsion amongst those two. Well, that is where they basically space themselves out so that they are opposite corners of one another. And that is the lowest repulsion that those two elements could have. So that is why we see these lining up in the same rigid pattern over and over again. And if you actually know about salt and table salt, you can crush salt, you can grind it up, and the crystalline structure allows you to do that, which is different than, let's say, a metal where it's more malleable and you can bend it. This rigid structure does not allow you to bend ionic compounds. A brief mention here on the formula unit, just the smallest piece. So in this example here, you have a formula unit. You might have a huge compound of salt. The formula unit is going to be the smallest piece of that ionic compound. And then how they're arranged. We basically talked here about this attractive and repulsive forces in the previous slide. Again, they are aligning themselves so that the positive and the positive are repelling each other, but at the greatest angle possible, which is basically, if you make a line 180 degrees, linear. That's the greatest repulsion that they can have. The last thing we want to talk about here that you need to know are polyatomic ions. These you're going to have to memorize. So a polyatomic ion is a group of covalently bonded elements with an overall charge. So this example here, nitrogen, this is NH4. Ammonia, or ammonium, with a positive charge. Nitrogen, non-metal. Hydrogens, non-metals. Non-metals bonded together typically form covalent compounds. It is a covalently bonded group. However, it has an overall charge, which tends to lead more ionic compounds deal with charges. So you need to know what a polyatomic is. It's a covalent with charge. And then also in your worksheets packet, you have this common polyatomic list. Take a look at it. You need to recognize some of these. I guarantee they're going to show up on your tests, on your quizzes. I would star all of these, but I'm not going to go through and do this. Study them. Know them. That's it for chapter 6.